Welcome to Electromagnetic Waves Module 2. Today I am going to discuss about Gauss law and divergence. This Gauss law is one of the fundamental laws of electromagnetism. So, this is the course outline, and today's lecture I am going to discuss about applications of Gauss law. So, as you already seen the point charge, line charge, sheet charge and volume charge by applying Coulomb's law. So, how we have derived the electric field intensity E by applying Coulomb's law. So, today we are going to see the Gauss law, and we are applying this Gauss law to these charge distributions. So, first let us see Gauss law. During the year 1777 to 1855, who was invented this divergence theorem? So, by using this divergence theorem, he explained what is Gauss law. A German mathematician who is called Friedrich Gauss, who was born in the year 1777 and died in the year 1855, who was developed the divergence theorem, and usually the divergence theorem is well known by his name as Gauss. He was the first physicist to measure electric and magnetic quantities in a proper unit. As I already told, this Gauss law is one of the fundamental laws of electromagnetism. And now, how to define this Gauss law? So, Gauss law states that the total electric flux, if you take a closed surface for a spherical system, a closed surface which is going to distribute the electric flux uniformly throughout the surface by taking some charge. So, at that point of time, the total electric flux psi through any closed surface is equal to the total charge enclosed by that surface. So, therefore, psi is electric flux which is equals to the charge which is for closed surface. That is, psi is equals to, for this closed surface, integral d psi, which you can equate with the electric flux density d into ds. So, that means that the total charge enclosed by that surface q is equals to integral rho v dv. So, or you can equate q is equals to integral closed surface d into ds, which is equals to integral over rho v dv. So, here for this equation, if we are going to apply divergence theorem to this middle term, it is going to be integral closed surface d into ds is equals to divergence theorem del into that electric flux density, that is d, del dot d into dv. So, by comparing these two equations with volumes, so you may have this integration will get cancelled. So, you will have rho v is equals to del dot d. So, by looking into these two equations, the first look at this equation. This equation states that first of the four Maxwell's equations which is going to be defined in future. And if you observe these two equations, or equation 5, which is going to state that the volume charge density is same as the divergence multiplied with electric flux density. So, rho v is equals to del dot d, which in turn fact that the rho v is simply taking at a point which is nothing but the volume charge per volume per unit charge at that point. So, that rho v is equals to del dot d. Now, after deriving this, you must observe some points from these two equations, that is equation 3 and equation 5. So, when you look at these two equations, so here these two equations are going to be stated Gauss law, and at the same time when you consider equation 3, it is stated Gauss law, but it is in the form of integration. So, whereas the equation 5 is also states that it is a Gauss law, but it is in the form of differential or point form. And once if you observe these 2 points, then you can say that after looking these 2 equations, which are nothing but Gauss law, and other alternative of this statement is nothing but Coulomb's law. So, how we are going to obtain this Gauss law through Coulomb's law means properly applying the divergence theorem to the Coulomb's law, you will get the Gauss law, right. So, then the third observation you must have, when you are applying this Gauss law to determine electric field intensity E and electric flux density D, it should obey the condition. So, which condition means it should be symmetric condition. When it satisfies the symmetric condition, you can able to apply this Gauss law to different charge distributions. So, first let us consider by applying this Gauss law to determine E or D, it should satisfy, when it is having charge distribution to different coordinate systems, it should satisfy symmetry condition. When you consider rectangular symmetry, if it is going to have the symmetry either on one of the parameter or component, which is either x or y or z. If you consider cylindrical symmetry, it should depend on rho, and other components are independent. When you consider spherical symmetry, it should depend on r, and theta and phi are independent in this case. So, finally, if you want to determine E or D by applying Gauss law, it should obey the symmetric condition. If it is not going to obey the symmetric condition, then as usual you can apply Coulomb's law to determine E or D, as we seen this in module 1. Now, we can take one example to apply Gauss law and how Gauss law is going to be existed by through that example. So, here you just see 2 closed surfaces we have considered, and each closed surface we named it as V1 and V2. When we consider V1, the net flux leaving from V1 surface is, you have 2 flux charges inside the V1, that is 10 nanocoulombs and minus 5 nanocoulombs. So, the net flux leaving the V1 after considering the Gauss law, it will be like 5 nanocoulombs. At the same time, you can observe that here 20 nanocoulombs and 15 nanocoulombs are outside of this closed surface of V1. So, the net flux only 10 nanocoulombs and minus 5 nanocoulombs are enclosed by this surface. So, that the net flux leaving from the V1 is 5 nanocoulombs. So, 20 nanocoulombs and 15 nanocoulombs are outside the closed surface of V1. So, this 20 nanocoulombs and 15 nanocoulombs, what it is going to contribute? So, these are going to be contributed when the net flux leaving or crossing from the closed surface V1 to free space. So, that means here it is obeying Gauss law, but whatever the flux present at the outside of the closed surface, which is going to help when it is going to cross from closed surface to the free space. And similarly, if you take the closed surface V2, here the net flux leaving from the V2 is 0. So why? There is no flux enclosed by this surface, so that the net flux leaving from V2 is 0. Now if you take the Gauss law, it is obeying that electric flux is distributed, that means charge distribution exists and which is enclosed by the surface. That is, electric flux is enclosed by the surface or uniformly distributed over the surface, and it has the charge distribution also. It is obeying, but the charge distribution from the closed surfaces V1 and V2 which are not symmetry. When it is not symmetry, then it is very difficult to find out the electric field intensity E and electric flux density D. Therefore, when you are applying Gauss law, it should obey that the charge distribution should have the symmetric condition. When it is not obeying this symmetric condition, then you should go with the Coulomb's law to determine electric field intensity E and electric flux density D. So, if you take the case study and you can verify whether Gauss law is obeying or not for this case study, right. So, that means you are applying Gauss law and we are taking the sphere for application of this Gauss law. So, let us check the results of Faraday's experiment. By placing a point charge Q at the origin of a closed surface and which is going to maintain the spherical coordinate system, and when it is a sphere, it should have the sphere of radius A. So, by taking these points into the consideration, you just apply the Gauss law and verify it. Now, we came to know what is Gauss law and how we can apply this Gauss law to determine electric field intensity E and electric flux density D. And also we have taken one example as a complete sphere which is enclosed with some dielectric medium. So, how the electric flux and the charge distribution taken place for that by applying Gauss law. Now, we are going to apply this Gauss law to different applications like point charge, line charge, volume charge and surface or sheet charge. So, for each one, how this Gauss law is going to exist or how we are going to apply this Gauss law to those charge distributions at different cases. So, let us see one by one. Before going to discuss about different charge distributions by applying Gauss law, you should know some points. So, when you are applying, as already discussed, when we are applying Gauss law, you should make sure that the charge distribution is maintaining symmetry condition. If the charge distribution is maintaining symmetric condition, then you can go with the construction of mathematical closed surfaces. So, what is this mathematical closed surface means? It is also known as Gaussian surface. Once if you construct the Gaussian surface, then you have to choose the surface that D, that is electric flux density, is either normal or tangential to the Gaussian surface. Suppose if the electric flux density D is normal to the surface, then D dot ds is equals to d ds, because D is constant on this surface, because D is normal to the surface. That is why if it is normal to the surface, D dot ds is equals to d ds. When D is tangential to the surface, then it is perpendicular. Tangential means, so d dot ds is equals to 0. So therefore, we must choose a surface that has some of the symmetry exhibited by the charge distribution. If not, we cannot. So by taking all these points into the consideration and apply these ideas when we are applying Gauss law to different applications. Now let us see one by one. So first let us go with a point charge. So you just see the diagram. So here this is a spherical surface and center is a point charge, point which is having some charge, that is Q, and this spherical is having some radius from the center of the point to the on the surface, which is having radius of R, and on the surface we have taken the point P, right. So when you are taking a point P to determine electric flux density D, you should make sure that your spherical surface, choosing a point on that surface, should have the symmetry condition. So we assumed that we have taken the point in such a way that we have taken the point on the spherical surface in such a way that it is maintaining symmetry condition. So therefore, a spherical surface centered at the origin is, we are considering it as Gaussian surface. So since D, that is electric flux density, is everywhere normal to this Gaussian surface, so therefore D is equals to dr into AR, right. So now once if you have defined what is D, then you can apply Gauss law and you can check what is D. So by applying Gauss law, what is Gauss law? Electric flux enclosed by the surface is same as the charge enclosed by that surface, that is psi is equals to Q enclosed. Okay. So now which gives Q is equals to, as we know, closed surface integral D dot ds. So what is D here? D is nothing but dr into vector AR. So dr is constant, closed integral ds. So this closed integral ds is nothing but your area of Gaussian surface, right. So how we are, this value is going to be 4 pi r square. How we are going to get the closed surface of the sphere? So the variables are theta and phi. Phi is going to be vary from 0 to 2 pi and theta is going to be 0 to pi, right. And for this spherical coordinate system, it is going to be r square sin theta d phi, as you well known, right. So the total value of this is going to be 4 pi r square, right. So which is the surface area of the Gaussian surface, as we calculated when we determine E for the point charge. So therefore if you substitute D from this, dr or D is equals to Q divided by 4 pi r square into AR, right. So which is same as what we determined in electric field intensity E and electric flux density D. So how we applied the Gauss law to this point charge? This is the basic application, and if you understand this, when we go with a line charge or volume charge or sheet charge, it will become easy. So then let us see the next charge, that is infinite line charge. When you consider infinite line charge, so here we have taken, suppose the line, the infinite line, this is infinite line, right. So which is having a uniform charge as rho along the length, some length which is L, so that the uniform charge is rho L coulombs per meter, and this infinite line charge is lying along the z axis. So once it is having, so you have to determine D, where that D should be at a point P which we have chosen on the surface of the cylinder, and at the same time we are assuming that this choosing cylindrical surface for the point P is maintaining symmetry condition. Therefore, D is constant on and normal to the cylindrical Gaussian surface. When it is on and normal to the cylindrical Gaussian surface, then your D is equals to D rho A rho. That is what written here. So now when we apply Gaussian law to this line charge, we are going to apply the Gauss law to an arbitrary length. It is infinite length, so that we are considering that infinite length as arbitrary length L of that line. So here the integration, that means by applying Gauss law, you will have what is charge rho L into L. Rho L into L is your charge Q. Q we can also define it as closed surface integral D dot ds. So what is D? D is nothing but D rho A rho. So when we consider D rho A rho, so D value we are substituting. So D rho is constant and closed surface integral ds. So what is this? This is the surface area of this cylinder. So that surface area of that cylinder is nothing but 2 pi rho L, right? And you just note that here the closed integral D dot ds you can evaluate on the top and bottom surfaces of the cylinder, which is going to be a 0, because cylinder there is no z component, only rho component exists if it obeys the symmetric condition, so that it has no z component, so that the integral D dot ds has for top and bottom surfaces it is going to be 0. Then since D has no z component, so that means D is tangential to those surfaces. So from that D is equals to L gets cancelled here, and D is equals to rho L divided by 2 pi rho. So this D is same as what we derived from the Coulomb's law for the line charge, which is same as that. So that means if you apply divergence theorem to the Coulomb's law, results which gives the result of Gauss law, right? So then let us go with the next charge distribution, that is infinite sheet of charge. So if you consider infinite sheet of charge, you just see this figure. In this figure, this is your infinite sheet of charge. So in this infinite sheet of charge, it has the charge of rho s coulombs per meter square, right? And in this we have to determine the electric flux density D, where at a point P which is located on the surface of the sheet, we have taken it as a rectangular box. And these two faces, rectangular box, if you consider that rectangular box, two faces are going to be symmetry or parallel to the sheet, and two faces are tangential to the sheet. So when we consider D is normal to the sheet, then D is along the z axis, so that and we have located the sheet in such a way that it is located on the plane at z is equals to 0, so that it is the rectangular box is along the z axis. So as D is normal to the sheet, so therefore D is equals to dz into Az. Once if you have defined D, electric flux density D, so you can apply Gauss law, which gives the value of your charge. So rho is integral ds, which is nothing but your charge, and this charge we can also define it as similar case in the by taking into the consideration of previous. So closed integral d dot ds, which is equals to, what is d? D is dz az. So dz of this ds, integral ds is nothing but the surface area. So if you consider here this surface area of rectangular box, if you consider the sides, that is left side and right side of this rectangular box is tangential to the sheet, so that it becomes, the area is 0. So only the top and bottom areas or surfaces are normal to the sheet, so that only we are going to consider top and bottom surfaces of the rectangular box. So that dz of for top it is integral ds plus for bottom it should be integral ds. So the area for top and bottom boxes we are considering it as A. So when we consider A, how it is going to substitute. So rho s A is equals to, here the A box of each box of having area A. So rho s A is equals to dz of A plus A. So this becomes 2A. So AA gets cancelled, D is equals to rho s divided by 2 into Az. Or you can also, as we know from electric flux density, D is equals to epsilon naught E. So from that E is equals to D divided by epsilon naught. Now substitute D value here, rho s divided by 2 epsilon naught into Az. So this is how we applied the Gauss law to determine the charge distribution for a sheet. Okay. So now the last application of your Gauss law is uniformly charged sphere, that is nothing but volume charge distribution. So now you just consider a sphere of radius A, right. So with uniform charge of rho v, because it is a volume. So uniform charge is having rho v coulombs per meter cube. Now for this spheres you have to determine D, that is electric flux density, right. So here for these two spheres we are constituting the Gaussian surfaces at different cases, two different cases. So one is here, if you observe, this is the radius from the inner circle, center of the origin, that means from the origin to the sphere it is radius r, and it has, for the outer sphere it is A. So that means if you take the condition, so here r is greater than or equals to A, this is one case. And if you take the second case, so here r is less than or equals to A, right. So for these two cases we are going to determine D, that also everywhere on this surface. And here before going to apply, we should ensure that whether this is having spherical symmetry or not. So here we are assuming that the charge has a spherical symmetry, and obvious that a spherical surface is an approximate Gaussian surface, right. So look at this, how to apply the Gaussian law. So when you are going to apply the Gauss law, you should take separately that r is less than or equals to A and r is greater than or equals to A. So two cases you have to take separately. So, first let us consider first case, that is for r is less than or equals to A, the total charge enclosed by that spherical surface of radius r is nothing but q enclosed, that is charge enclosed by that surface is equals to integral rho v dv as we know. So, which is equals to rho v integral dv. So, rho v, what is integral dv? So, this is a spherical surface. So, for spherical surface you have r component, theta component and phi component. So, r is nothing but 0 to r and r we are considering it as a, and theta is from 0 to pi as we know, and phi is from 0 to 2 phi. So, which is going to be r square sin theta dr d theta d phi, right. So, if you simplify this, you will have surface area of the sphere when r is less than or equals to a. So, which is going to be rho v 4 by 3 pi r cube. And what is psi? As per Gauss law, psi is equals to closed integral d dot ds, which is equals to what is d? dr ar. So, dr closed integral ds. So, which is equals to dr closed integral ds, that means surface area of the spherical, or we can say that spherical surface area, which is as already known, we calculated this spherical surface area for point charge, which is nothing but 4 pi r square. So, therefore, psi is equals to dr 4 pi r square, which is also q. So, now hence psi is equals to q enclosed. Now, equate psi value is dr 4 pi r square and q enclosed is rho v 4 by 3 pi r cube. So, now equate these two. So, you will have d is equals to here 4 pi gets cancelled, r square only one r will be there. So, dr is equals to r by 3 rho v into ar, and you can see here this r is varying from 0 to a. R is, after saying this, r is from 0 to a, right. So, keep this in mind. Next case, when we consider r is greater than or equals to a, the Gaussian surface is this. So, by taking that Gaussian surface into the consideration, here the charge is going to be enclosed by the surface, which is the entire charge in that, in this case. So, q enclosed is equals to integral rho v dv, which is equals to rho v integral dv. So, and this integral dv, as we discussed just now in the previous case, when r is less than or equals to a, you will have 4 by 3 pi a is your radius. So, pi a cube. Okay. So, now what is required? Psi is required. So, what will be the psi? Psi is equals to integral over d dot ds. So, which is going to be dr, as we know, integral, closed integral ds is equals to 4 pi r square, that is surface, spherical surface area. So, now you equate psi is equals to q enclosed. So, when we are going to equate psi is equals to q enclosed, dr 4 pi r square is equals to 4 by 3 pi a cube rho v, right. So, if you cancel 4 pi, d is equals to a cube divided by 3 r square into rho v into ar. So, this electric flux density we obtained for the case r is greater than or equals to a. So, therefore, the equations, from these equations, so you can observe that d, that is electric flux density, is everywhere. So, d is everywhere. So, which is like what is this D? So, D is equals to, you have R by 3 rho V A R we obtained during R is in between 0 and A, and if R is greater than or equals to A, the electric flux density D is equals to A cube divided by 3 R square rho V A R. So, that means you just notice from this equation that we can have the ability to take D out of the integral sign, which is the key point to finding D by using Gauss law. So, in other words also you can say that D must be constant on the Gaussian surface. If not, it is going to be bit difficult to obtain the D, that is electric flux density, by applying Gauss law. So, today's lecture we have discussed about what is Gauss law, and when we take some example like two closed surfaces, how we applied the Gauss law or how the Gauss law holds for that example, and at the same time when we are going to apply Gauss law, it should maintain the symmetric condition. When it is not going to maintain the symmetric condition, then it is not possible to apply Gauss law to determine E or D. So, at that point of time we should apply Coulomb's law to determine E or D. And at the same time we have seen the case study, and after that we have gone with the applications of Gauss law. When we consider applications of Gauss law, where we applied this Gauss law means for the charge distributions of point charge, line charge, surface charge and sheet charge, right. So, next lecture we will go with the divergence, then what is the Maxwell's first equation in terms of electrostatic, and then the operator del and divergence theorem. Thank you.